So hello, welcome to our lecture 10 of group theory. The in this lecture we'll start from a theorem, from proving a theorem. The theorem states that let G under binary operation dot be a semi-group containing a finite number of elements in which both the cancellation law hold, that is A compose B equals to A compose C implies B equals to C, and B compose A equals to C compose A implies B equals to C. Okay, the main thing here is the number of elements is finite. There is a finite group, so there is a finite number of elements in the group, or all this proof can be done. If all these conditions holds, then the semi-group becomes a group. We have to prove that. Now let's do the proof. Let there are n elements in the group G, say A1, A2 up to Am, then the elements of the form A compose A1, A compose A1 compose A2, A2 A1 compose A3 up to A1 compose A all belong to the semi group G, and I have considered n elements from the semi group G, not group G. Here now it is a semi group, we have to prove it's a group. So there are n these all elements are belong to the semi group G, and all of these elements are A1 compose A1, A1 compose A2 are distinct, because if any two of them say are equal, say A1 compose AI equals to A1 compose AJ for AI not equals to AJ, obviously, then but from left cancellations law we can say what AI is equals to AJ, so which contradicts our method. This which contradicts our assumption that AI is not equals to AJ. So all these elements A1 compose A1, A1 compose A2, A1 compose A3, A1 compose AN are distinct. Now since G contains n distinct elements and they can be written as A1 compose A1, A1 compose A2 up to A1 compose AN, like this. Therefore the equation AI compose X equals to AJ has a solution in G, i.e. for AI, AJ belongs to G, the solution X belongs to G for this equation, and this one will be A1. The equation of form A1 compose AX has a solution, and A1 and AG are belongs to G, where J equals to clearly equals to 1, 2, 3 up to N. Considering the elements of form A1 compose A1, A2 compose A1, A3 compose A1 up to N compose A1 will be similarly be all distinct, because if for any two AI not equals to AJ, two distinct elements of the semi group, we let's wait, considering ai equals to not equals to aj for any two distinct elements, and if somehow a1 from this, if any two of them equal, we can say a1 ai equals to a1 compose aj for some ai and aj, but ai and aj are not equal since they are n distinct elements. By sorry, this should mean ai compose a1 and aj compose a1. It should be written like this, and we will apply the right cancellation law. What we will get from here, that what we will get, ai is equals to aj. That was contradicting our assumption that ai not equals to aj, since there are n distinct elements. ai should not be equals to aj, and therefore this all these terms a1 compose a1, a2 compose a1, a3 compose a1, all this of this should be distinct. Now the equation of form y compose a1 equals to aj, where j equals to 1, 2, 3, 4 up to n, has a solution in G, has obviously a solution in G, i.e. y belongs to G. So from here what we are getting, G naught is G under binary operation naught forms a semi group for which for any two arbitrary elements a and b belongs to G. The equations a naught x, a compose x equals to b, and y compose a equals to b has a solution in G. So from previous theorem, what we can say, from previous theorem of this condition, we can say G under a binary operation not will form a group. So our proof is done. There is an important note now. The theorem does not hold if G contains an infinite number of elements. Example, set of all natural number under operation multiplication forms a semi-group in which the cancellation law holds, both the cancellation law holds, but if we check, we will find that in the set of all natural number under binary operation multiplication doesn't form a group. Since we can give a reason that since in the set of natural number is infinite set. The next topic is alternative definition of a group. The definition says that let G be a non-empty set satisfying the conditions 1. G is closed under binary operation not, 2. Not is associative, 3. There exists an element E in G such that E compose A equals to A for all A in G for each element A in G there exists an element A dash in G such that A compose A dash equals to E. So what it means to say, if there exists, then it will form a group. Then what the theorem, the definition means to say that if for any set G under binary operation it satisfies one closure property, two associative property, and left identity property, and along with the left inverse existing of a unique left inverse property, then it will form a group. Or similarly, we can write a definition as, if it satisfies the closure property, it satisfies the associative property, it satisfies the right identity property and the right inverse existing of unique right inverse, then it will form a group. So let me do the proof that if some set satisfying this property will form a group. So we have G under the under binary operation is a semi group since it's satisfying both the closure and associative property. And E is the left identity of the group, and each element A belongs to G has a left inverse. So now to do the proof, we have to first prove that this E, which is the left identity, is actually the identity element of the group, and we have to prove that this A dash, which is the left inverse of A, is actually the inverse of A. So to do that, first taking another since every element of the group semi group has a left inverse, so A dash which is the left inverse of A, well obviously A dash will belongs to G, so it will also have a left inverse, say A double dash with a left inverse of A dash in G. Then we have from the property A double dash compose A dash equals to E. Again we know A dash equals to A dash compose A equals to E from the given because A dash is the left inverse of A in G. Now this, if we write A compose A dash, if we find it as E, then our proof is done, because we already have A dash compose A equals to E. If this becomes equals to E, then this equation will be this will form an equation like this: from A dash compose A equals to A compose A dash equals to E, and since A is arbitrary, from there we can say that there exists a unique inverse. So now let's see, A compose A dash equals to, this can be written as E compose A compose A dash. Since E is the left identity, we can write it from here. Now E can be written as a double dash compose a dash. We have shown this before. Compose a dash. Now from associative property, we can write it as a dash compose a. We're taking the bracket here and a dash outside. Now this can be written as E. So this will become a double dash compose E compose a dash. Now this is the left identity again, which will become equals to a double dash compose a dash. Now a dash is the left inverse of a dash, so this will become E. And again we can see a compose E. Oh, look, wait, we are making this as equation, so we are having a compose a dash equals to E. We are making this as equation A. Now next we again have a compose E equals to a compose a dash A. We have, because since A is the inverse of a dash is the left inverse of A, so we can write a compose A equals to E, where E is the left identity, whatever. Now this will be equal by associative property. This can be written as a compose a dash compose bracket, this putting this in bracket by associative property, and this again can be written as for E compose A from equation A. And now this E compose A can be again written as E, since E is the left identity of the group, of the semi group. Sorry, this can be written as A, whatever. So now what we have, A compose E is equals to E compose A equals to A. For, and since A is arbitrary, this proves the A is arbitrary. This proves the existing of unique identity element in the of the semi group G. And we have already proved that A dash equals to A is equals to A compose A dash equals to E for any where E is the identity element. We have proven that. We have to first prove the E is the identity element, because if we here we have already proved that A compose A dash equals to E equals to A dash compose A equals to E. We have already proven that, but we can't tell this that this is at this stage this is the existing of unique inverse, because at this point this is a left identity. But now here it has already become an we have proved that this is not left identity, this is actually the identity element of the semi group. So we can say that this, and there is this A dash compose A equals to A compose A dash equals to E, where E is the identity equals to E, where E is the identity element. And since A is arbitrary, we are finding that for any arbitrary element A belongs to the semi group, there exists a unique A dash such that this property is satisfied. So existing of unique inverse is also satisfied. So all the four properties of properties existing of the closure property, the associative property, the identity property, and the inverse property also are satisfied. So the semi group is under the semi group is actually becoming a group. Okay, I will end my lecture here and do some more worked out examples and more examples in the next lecture.